Good morning, friends. And on this lovely, lovely morning, we are to be regaled even by Graham Davey, who has the intriguing title of Why Teach Maths? Graham.
Thank you very much, Ray. The original title was Let's Stop Teaching Maths. I recalled that the first talk I gave to this group was called Let's Sell All Our Buildings. I think I made it quite clear during the talk.
I can't hear very well, Graham.
Is there anybody else who's finding it difficult to hear?
Yeah.
You're not loud. Can you get closer? I can hear you well enough.
Yes, it is very quiet.
I'm using a headset microphone, which is normally better than the computer microphone.
I really can't make anything out. Sorry.
Hattie, I've muted most people because other people tend to interfere with noises during talks. And Hattie, you're usually one of the worst offenders. Let's see how it goes.
Okay, can you hear me now? You have a volume control for your loudspeakers. I can't control the loudness of what I am sending out. I was saying that the first talk I gave to this group had the even more provocative title of Let's Sell All Our Buildings. I made it clear during the talk that I didn't want to sell all our buildings. In fact, I didn't anticipate any meeting houses being sold if they were proving viable and useful. But I was having a conversation with a Bedminster friend recently, and the subject of meeting houses came up. And she said, well, of course, we all know what you think about Quaker meeting houses. And I said, what do I think about Quaker meeting houses? She'd taken the original title, had not heard what I had said, and just assumed that I was arguing for all meeting houses to be sold off and Quaker meetings to flourish without buildings. So this talk is subject title is Why Teach Mathematics? And what prompts it is the feeling that very few people in everyday life use any mathematics beyond what they have learned at junior school. And yet all this time and effort goes into presenting a subject which has great status, but really not much usefulness to most people in secondary school education. What I would certainly argue for is a thorough teaching of the basics. And the basics of mathematics are best learned early on in the junior school. Particularly, I would say, memorizing multiplication tables. So many children in secondary school have this fear of mathematics because 9 times 7 is a problem to them. It's not a problem to me because when I was about 6 or 7, with other children the same age, I chanted the multiplication tables time and time again, and they are drilled into me. So I don't have to think about them. They cause no anxiety. The answer is just there. And I would like that kind of confidence to be more widespread in our secondary schools. I would want also, again, taught in junior schools, primary schools, a facility with numbers, particularly things like place value. Why is it that with a whole number, when you add a naught, it gets 10 times bigger? And when you add a naught to a decimal number, it doesn't make any difference at all. the size is the same. You've got to understand this, where these processes like shifting the decimal point or adding noughts, what effect it has on the digits which you started with, in moving from one column to another, and therefore changing value. The 4 rules with decimal numbers. The children at primary school may not be entirely happy about, for example, dividing one decimal number by another decimal number. And they counteract at secondary school with, why do we have to do this? Because we've got calculators. Well, I would say, don't place all your trust in using a calculator. I remember with a group of intelligent, well-educated adults trying to get them to work out their energy consumption. And one person quite seriously thought that because the calculator said so, that she was using 100 times as much energy in her car as she was in heating her house. Now that is obviously nonsense, but she didn't accept this. And it took me some time to convince her that she got a decimal point in the wrong place. You get the same kind of attitude today in our belief and trust in computers. 736 postmasters and postmistresses were accused of fraud because the computer said that money was missing in their accounts. And everybody trusted the computer rather than the 736 honest and innocent human beings who were the victims of an appalling scandal. So in teaching facility with numbers, okay, use your calculator, but look at the numbers first and make an estimate, round them all off to round numbers, and write down what you think the answer is going to be roughly, and then do it on the calculator. And if those 2 numbers are wildly different, something has gone wrong, and it may well be the buttons you press on your calculator rather than your intelligent approach to an estimation of the answer. All the ways in which we represent numbers less than 1, decimals, fractions, percentages, all equivalent ways of giving the same quantity, a number between 0 and 1. And you've got to be able to transfer from one to another and understand what's going on. And particularly percentages. We are bombarded with percentages nowadays. I'll say a word about this later on. But particularly during the pandemic and all the news reports we've had about numbers of people affected and the numbers dying, the numbers recovering and long COVID and all the rest of it, percentages come out. And they are misused. And children, certainly adults, ought to know and be familiar with the use of percentages and the misuse, sometimes deliberate, more often accidental. Now, not all these basic aspects of mathematics can be covered fully at primary school. This is where the foundations are laid for education at secondary school. And at the moment at secondary school, they don't pay as much attention, I think, as they should to useful mathematics. Mathematics develops into algebra, geometry, trigonometry, calculus, set theory, Boolean algebra, hyperbolic functions, and then in applied mathematics, statics and dynamics. And the amount of this material which you're actually going to use if you're going to be a a lawyer or a trader of some sort is very, very little. Every maths teacher gets assailed by students who say, why have we got to learn this? And it's very difficult to give an answer to a boy or girl who is not going to be a mathematician and probably doesn't want to be a mathematician. And all one can say is that mathematics is treated very seriously, perhaps over seriously, whatever you're going to do in the future. And to get a qualification, you've got to pass an exam, and this will be in the syllabus. It's very unsatisfactory, and it reminds me of the ultimate cynical view of education, of casting artificial pearls before real swine. It's the artificiality of the pearls. I certainly don't want any person who has an aptitude for mathematics and wants to study it should have the opportunity at secondary school. But to inflict all these branches of a vast subject on all children at secondary school level, I think is misguided. Now, what should students do at secondary school? First of all, I would want all of them to keep up the basics of primary school mathematics education, things I outlined before, and to develop them and to teach them so far as possible by relating them to other subjects that they are doing and to what is going on in the world, what can be picked up from the media and television and press and so on. So there would be more work on percentages, comparison, and change, including the ambiguous cases where percentages are used. For example, a percentage change in a percentage. Now you get this quite often. A news report says that 20% of the population die from a certain disease. A new drug has been introduced which reduces this likelihood by 10%. What does that mean? Does it mean that 20% goes down to 10%? Or does it mean that 20 is reduced by 10% and goes down to 18? It's ambiguous. And you get it again and again that a percentage is subject to a percentage change. The key question which children should be taught to ask is percentage of what? The trouble is we use the word percentage without saying what it applies to. And that is the crucial question. Unless you can answer that, the statement is ambiguous. So basically, reinforcement and development of the basics of what is essentially arithmetic, of course, it's not mathematics, at secondary school. But I would want all secondary school students as well to have some introduction to the beauty of mathematics. For many students, this is a contradiction in terms. Mathematics is a source of anguish and horror and fear. The idea that it can be beautiful would be completely alien to them. And yet I think it is important. For example, seeing algebra as a language. In preparation for this, I took a simple result in mathematics called the distributive law. It's very simple. And I wrote it out in English. And then I wrote it out in the symbols of algebra. In English, the English language, it took 126 characters. In algebra, it took 12 characters. So algebra as a language is 10 times more efficient at conveying a truth than is the English language. And of course, the further you go in algebra, the more impossible it is to express it in terms of the English language. You have to resort to symbols. On the subject of the beauty of mathematics, I'm looking at the two irrational numbers or transcendental numbers in mathematics, one of which you know something about. That's called by the Greek letter pi. The other one you may not be familiar with is called e. Now e, the exponential number or function, is much more important in mathematics than pi is. But it goes well beyond my knowledge, so I'm not going to discuss that. Associated with it is another so-called number by the letter I. Now I stands for imaginary, and I is the square root of -1. What is the square root of -1? What number multiplied by itself gives you -1? And the answer is I. It doesn't exist in the real world. It is purely imaginary. And yet in mathematics, combined with E, it is very, very important in developing a branch of mathematics which can achieve the proof of results which cannot be obtained in any other way. They are true, but their proof depends on the creation in the mind of something which doesn't exist. I find that fascinating. But we're going to look at the other irrational number called pi. Irrational means it's not a real number. It cannot be expressed as a fraction. There are approximations, of course. It cannot be found, it cannot be calculated as a root of an equation. There is no equation which produces pi as a result. All one can do is to find its value as near as one needs it by a series of approximations. Writing it out, it is a number just more than 3, and it's a decimal number, and it goes on forever. There is no pattern in the succession of digits, and you can, with modern techniques and computers, you can get the value of pi to thousands of places of decimals. 4 is usually enough for most people, 3.1416 or 3.14159 is the useful value, and that's normally accurate enough. Now I'm going to start my PowerPoint presentation, except it's not PowerPoint, it's a piece of paper on a music stand. In order to see it, you will need to have speaker view. So go to view in the top right-hand corner of your screen. If you're on gallery view at the moment and seeing lots of small faces, that will be no use to you at all in seeing what I'm about to put in front of the camera of my laptop. So go to speaker view, and shortly you should be able to see what I want you.
Slightly embarrassingly, Graham, in speaker view, this appears mirror reversed to us. We are not seeing it reading right to left. We're seeing it the wrong way around. So that's why you're seeing puzzled looks on Jenny's face and so on. I believe that only you can correct this. Oh, that's better. How did that happen? Good.
I wrote this out.
All I can see at the moment is David, which is
If you pin Graham rather than just do speaker view, you will get just Graham large on your screen.
I don't know what to do about this. I've got it on this piece of paper, both in normal,
that's okay.
normal view. And
That's okay now. That's okay.
Carry on, Graham. You're doing very well, mate.
Well, you're looking at the back of what I wrote out.
That works.
But
That
anyway,
works.
if you can see it, that's fine. You're missing the diagram, but I can describe that. Right, we start in the top left-hand corner with the relationship between the circumference of a circle and its diameter. And in the classroom, of course, one starts with circles of different sizes and measuring the circumference and the diameter, and noting that the bigger the circle, the bigger both of those quantities are. Not easy to measure circumference and diameter of a circular coin, but when you got onto a plate, saucers, cycle wheels, you get more accurate results. And you hope always that some member of the class will suggest dividing the circumference by the diameter. And when you do this, of course, you get more or less the same number, just over 3. If you multiply both sides of that equation by d, the d's cancel out in the fraction, and you get circumference equals pi times diameter. And then if you divide both sides by this number, pi, c over pi, circumference divided by pi, is equal to the diameter. Now imagine that you have a piece of string 25,000 miles long, and you tie it round the Earth at the equator. So the diameter of that circle of string will be 25,000 miles divided by pi. And I called that D1. That's the diameter of the Earth at the equator. And the diameter of the circle of string which you've tied round the Earth. Now cut the string and add in 1 extra yard of string. So now when you walk round the equator, lifting the string away from the surface, the same distance all the way round those 25,000 miles, you have a circle of 25,000 miles plus 1 yard divided by pi, and that is the diameter of the increased length of string. And I call that D2. Now, you can split this into two fractions because the bottom number, the denominator, is the same. So you would simply add the two top numbers to 25,000 miles plus 1 yard, and now split into two fractions. And that is another way of saying the diameter D2. But that fraction we've already met. That is the diameter of the Earth. So D2 is the increased diameter of the string due to this minute increase in length of 1 yard. To get the distance between the surface of the Earth and the string, you would separate, you would subtract the diameter of the Earth from the diameter of the string, and you have to divide it by 2 because that's the gap on both sides of the Earth. And if you do that, you get that distance, that gap between the Earth's surface and the string is 1 yard divided by 2 pi, or 36 inches divided by 2 pi. And that comes to 5 3/4 inches. And it's rather surprising that that minute increase in the length of the string should cause such a large gap when it's spread around a distance as large as 25,000 miles. I'm assuming that this can be seen as I intend. The second way in which pi comes into mathematics is not just related to a property of every circle, whatever its size. It also comes as the sum of an infinite series. I've taken just 3 examples from hundreds of ways in which pi can be calculated. The idea of an infinite series is something which goes on forever, but gives you gradually a finite sum, a finite total. Notice that the mathematicians who produced these all come from the 17th century. Let's look at the first one, which is Leibniz series. Pi over 4 is this string. There are alternate subtraction and addition signs which show how the total oscillates around a fixed point the further you go. If you take just one term, then you've got pi over 4 equals 1, multiply both sides by 4, pi equals 4. Now that's much too big, we know that, but take the second term and include that, take away 1/3, and that gives 2/3, multiply both sides by 4, and you get 8/3, 2 2/3. We've gone from 4 to 2 2/3. One is much too big. The second one is too small. but not that much too small. Take the next term and you'll get closer still. And the more terms you take, the more accurate the total comes to pi over 4. So this is an example of an infinite series using addition and subtraction. Others use simply addition, and sometimes there are two infinite series of that sort which have to be calculated together. The next one by the Leibniz, of course, is German. John Wallis was an English mathematician in the 17th century, and one of his versions is a product containing nothing but multiplication all the way through. But the multiplication fractions, starting with 2, and then getting gradually closer and closer to 1. So obviously, the further you get, the closer you get to 1, and the less and less effect that fraction has on the ultimate total. And then this, the last crazy one, he actually produced this in fairly early in his life, in something like the 1640s. And it's a single fraction, which of course goes on forever. These 3 dots mean you don't stop. They go on for an infinite distance or number of terms. So in order to calculate pi from this fraction, you've got to cut it off somewhere and then gradually work up. And again, you get this value of 3.14159. And I think in the 17th and early 18th century, for some mathematicians, the calculation of pi was an obsession. And they spent, well, one case, German mathematician called Eulen, he spent most of his life wrestling with the calculation of pi, and eventually got it to 23 decimal places and had it inscribed on his tombstone as his life's work. Since then, of course, pi has been calculated to very much higher values, but that is the only way in which pi can be calculated. It's an approximation from an infinite series. The third way in which pi comes into mathematics, apparently completely unrelated either to the properties of a circle or to infinite series in algebra, is by linking it to probability. And this time we have the French mathematician, Georges Louis Leclerc was his actual name, but he became Comte de Buffon, usually known as Count Buffon or Buffon, as he discovered that you can get a value of pi by dropping needles on a series of parallel lines. And if the distance between the lines is w and the length of the needle is l, obviously the needle can either fall crossing a line or in the gap between them, then the value of pi is 2ln over cw. Now l is the length of the needle, w is the width between the lines, n is the number of needles you've cast down, and c is the number which fall crossing a line like this one. Just to simplify it, if you make the length of the needle L equal to the width between lines, then these cancel each other out and you get pi equals 2n over L. Now turning that up the other way, dividing both sides by n, dividing both sides by pi and by n and multiplying by c, you can move these diagonally across. It's just one fraction equals another fraction. Pi over 1 equals that fraction. By multiplying and dividing both sides by the same thing, it's equivalent just to moving these diagonally. So 2 over pi equals c over n. C over n is the number of needles crossing a line divided by the total number of needles thrown down. So in other words, that is the probability of a single needle falling, crossing a line. And pi is calculated then essentially from the probability of a physical event happening in a certain way. So the point I'm making is that there is a case in secondary schools for pupils to be taught something about the beauty of mathematics. In this example of an irrational number, pi, entering mathematics in 3 apparently totally different ways: property of a circle, the limit of an infinite series, and throwing needles down on parallel lines, and the probability of the needle crossing a line. It's just an example of the astonishing world which mathematics reveals. I have in fact done this with a class. Normally the floor of a classroom doesn't have parallel floorboards. I find myself in one which did, or I arranged a swap so that I got to use a particular room. And we cleared the desks to one side. I had, I think, specially purchased a bag of nails, all the same length, and the children set about throwing these in a random way. Of course, to get a completely random way, they would have to be blindfolded. But the idea of 30 children in a room, blindfolded, throwing nails around, I think would have horrified any health and safety people, had there been any in those days. And we got a reasonably accurate result. So I hope the children were convinced. Now, I just want to finish with my main point, which is that it's very important that secondary students are taught statistics in schools. That is the one aspect of mathematics which I would want to be given much higher priority than it is at present. And one reason is that we are bombarded with figures, with statistics from political pundits and advertisers and so on. And the more you study statistics, the more skeptical you come about the ability to draw any conclusions from numerical research. I want to finish with a story. For that, you just need a little bit more knowledge about statistics and, and probability. Probability is measured on a scale of 0 to 1. So it can be represented as a fraction or a decimal, or very often as a percentage. And if you're a bookie, it's represented by odds as well. So a probability of 1/10 is, in bookies' terms, that odds of 9 to 1 against. But we'll stick with fractions for the moment. If you have a perfect die, that is a cube, which is perfectly uniform, and the numbering of the faces from 1 to 6 doesn't cause bias in any way, then when you roll that die, the probability of getting a 6 is 1/6, 1/6. If you have two perfect dice and you roll them together and you get 2 6s, the probability of that is 1/6 times 1/6, which is 1/36, very much smaller. And the reason for that is that there are 36 possible results when you roll 2 dice. For example, 9 can come from a 4 and a 5, or a 5 and a 4, or a 6 and a 3, or a 3 and a 6, and so on. And there's only one way in which you can get 2 6s, that's a 6 and a 6. So its probability is obtained by multiplication, 1/6 times 1/6, which is 1/36. The story concerns Sally Clark. Sally Clark was the daughter of a police officer, trained in law, and was practicing as a solicitor, so pretty well off, very nice home, husband, and practice in Cheshire. In the 1990s, she had a son, Christopher. Christopher was found dead in his cot at the age of 11 weeks. And that was put down to being a cot death. Unexplained at the time, but it just happened very rarely. Sometime later, she had a second son named Harry. He died in the same way at 8 weeks. And then Sally Clark was arrested and put on the trial for the murder of both her sons. A key expert witness at the trial was Professor Roy Meadow, a pediatric pathologist. And he said that, probably on good evidence, the probability of a cot death of a baby born of intelligent, well-adjusted parents in an affluent household was 1 in 8,543. And he accepted that was possible in one case. But in this family, there were 2 cases. So he said the probability of this happening by chance, by innocent cot death for 2 babies was 1/8,543 times 1/8,543. This comes to 1 in about 73 million. And he likened it to backing an 80 to 1 outsider and winning 4 times in succession. The trial was being conducted by a judge, barristers, and the jury, of course, all relatively well educated, some of them highly educated, but that argument was accepted. And Sally was convicted of the double murder and sentenced to life imprisonment. Various people were unhappy with this. and an appeal was mounted. The appeal was heard by a different judge, and again, highly educated barristers and so on, and they upheld the original conviction and therefore the sentence. And Sally's imprisonment continued. Eventually, the Royal Statistical Society was involved, and they pointed out that Roy Meadows' argument was flawed because the two events have to be completely independent. And the second cot death of Sally's baby was not independent of the first. It took place in the same home. There might well have been genetic connections. The way in which Sally handled her babies may have contributed in some way. Nobody was justified in assuming that they were independent events, and therefore the probability of murder was very much less than Meadow had indicated at the trial and was considered at the first appeal. A second appeal was held, and the appeal was upheld, and Sally was released from prison after over 3 years. The experience for her of that 3-year imprisonment destroyed her. A prisoner who is deemed to be guilty of harming a child is treated very badly by other prisoners. And also the fact that she was still claiming to be innocent was meant that she didn't get any privileges normally given to prisoners who accept the result of their conviction. So although she was out of prison, she was a different, very much changed woman. She became addicted to alcohol, and she died in 2007 at the age of 42, totally destroyed by a statistical mistake by a highly educated professor who had not been taught statistics at school. So that's my main argument. You could apply it to the 736 sub-postmasters as well. Is it likely that so many employees previously innocent should suddenly start acting in a criminal way? These questions were never asked, and all because we don't learn statistics at school. So that's all I want to say. I hope if you get opportunities to press for better, more relevant education in mathematics in the future, you will do so. You will take the opportunity. Thank you.
Thank you, David. David, Graham. Thank you, Graham. A very relevant and interesting presentation. So I would now ask friends for questions and comments to David.
David, I was absolutely enthralled, and really, I don't know why I said David. I hope I said Graham. But I was so fascinated and so sad that most of my life hasn't had that kind of understanding. I mean, like you, I did learn all my tables, etc., to an excellent level, but I never took it beyond a very basic O-level maths, and I didn't really understand the maths part of it at all. What I wanted to ask you particularly is there by any chance a book you would recommend that would take someone a bit further than O-level maths and to to just more information about what you were saying.
First of all, it's a privilege to be confused with David Saunders. I'm honoured by that, but my name actually is Graham. And I'm sure there are plenty of books which popularise mathematics and would be of interest to anybody who wants to improve on the kind of education they had at school. But I'm totally out of touch now. The one I have used to get some of the facts of my talk is Mathematics in the Imagination. I think that was produced in the 1950s. I had it at school with other mathematics students who put on an exhibition which aroused some interest. But there will be many others now, I hope, which excite your interest in mathematics without committing yourselves to things you don't need and don't understand.
Thank you very much. Thank you.
Yeah, Mary.
I've got a question from the lofty heights of Southmead Hospital. Marcus Millington asks, why is mathematics not better taught in school?
Yeah.
I think the main trouble is that we are dominated by universities and examination boards for whom relatively advanced mathematics is seen as a kind of key to success in life. I would point to the vast number of the population who are very successful in life and know relatively little of mathematics and use it even less. As I said at the beginning, there's not much you actually need to be successful that you haven't covered in primary school. How to get that culture changed, I really don't know. There are, I suppose, not enough people. Say every specialist in a subject wants their subject to be taught, and then the more people involved in learning the subject, the further they go in academic prowess in that subject, the better. And people are very reluctant to think, why am I teaching this? Why is it deemed to be so important when most of us manage without it? I feel better for that. Did any of you have really good experiences of learning mathematics at secondary school? David?
Well, Richard raised his hand before me.
But you might have been answering Graham's question. Maths was the only A level I got. I got maths and advanced maths at O levels, but I wasted my sixth form. But the maths was the only A level I've actually got. I got another 2 O levels that I didn't really need. But so yeah, maths was my strong point. But in usage, it's been arithmetic as an accountant. I did learn statistics, and I did understand it at the time. And it kind of doesn't matter how well you're taught something, unless you use it, you will lose that understanding. And I think, as you were pointing out, that the reason that the biggest thing, I mean, you lost me on pi when you got to the Comte de Buffon or whatever, but the statistics stuff, it really is important, because everything we see today about in politics and the world has got some mathematical basis, and people are misunderstanding that. They don't understand risk. They don't understand the difference between real probability and what they think is likely. It's a and people make big decisions about their lives, misunderstanding these important distinctions. And I think that the answer to teaching maths better in schools is not to teach it as a separate subject, but to build it in to the way people are understanding other things. We used to have, even at primary school, comprehension. You know, read a newspaper article and explain what it meant. And that kind of analysis in the school setting of topical stories and trying to understand them combines, it's multidisciplinary. It's not just maths, it's not just English, it's not just science or whatever. It's actually understanding all these things put together. And I think that's one of the things we've lost you tend to lose at the secondary school level. At the primary school level, you have a much more multidisciplinary approach, and children are learnt to use resources in different ways. You get to secondary school, you're put into boxes and you learn this discipline or that discipline, and the multidisciplinary stuff tends to have got forgotten. And the only way you're going to get maths at the level we're talking about understood by the general population is if they understand its relevance to all the other things they're learning. In my humble opinion.
Any other comments?
David.
Yeah. Well, just to go back to the glitch we had at the beginning, if you look in your settings for Zoom under video, you want to tick mirror my video, and it should be okay. You will see something mirrored on your screen, but other people will see it the right way around. But that's not the point. I think I loved mathematics at school. I loved chemistry. I loved physics. Maths appeared in metalwork and in woodwork. It appeared in sports. It appeared in history. It appeared in geography. It appeared in everything. And what to give you a statistic that ought to scare the hell out of you, 1/3 of American millennials do not believe the earth is round. Now, you can laugh about this, but this is 1/3 of American millennial children, that you can put that as percentage if you like, believe the earth is round. Of the people, don't believe that the world is round, of the people who believe that the earth is flat, 57% of them, 52% of them, that's over half of them, would say that they are very religious. In other words, they are committed to learning about beliefs and thinking that beliefs are as important as scientifically validated, evidence-based facts. And if you are seriously presenting a talk on the topic of we should teach less mathematics, then I would introduce immediately, I would raise my hand and say, I want to do a talk saying that the teaching of religion should be banned immediately from all schools, right? And that we should only teach critical thinking and humanist beliefs. And we should not teach people that what you believe is as important as what is actually verifiable and true, because the world is descending into a bottomless pit at the moment if people genuinely believe that the earth is flat. And on TikTok now, one of the channels on TikTok is devoted full time to people sitting there saying, is there anybody who is a flat earther who wants to talk about it? So it's an opportunity to debrief people who have programmed themselves into thinking that the earth is actually flat. So this is, I'm horrified that the extent to which we have stopped believing the importance of teaching science and so on. I could go on, I'll stop there. I think this is immensely worrying that that we're descending into anarchy, chaos, and ignorance at the moment. And teaching less mathematics, I don't think, is going to solve the problem.
The a small story which I think might amuse everybody is a mate of mine who used to teach maths at an East End junior infant school, and he got very frustrated for a while because the children weren't understanding the simple statistics he was presenting. But then he realized that at least 3 of the young lads there would take the betting slips that their father gave them to the betting shop. And he said, but you do horses. And the little lad done the statistics within a few moments. And the teacher said, but that's maths. And the little lad, 2 little lads looked at him and said, no, that's betting. Quite remarkable how that in everyday life that happens, but to them it was, you know, that's my amusing thing of the day. Thank you.
Christopher.
Yes, I was thinking, I mean, maths was my subject, although I'm not sure I ever understood it, but I do remember when the lottery first came out. Of course, being a Quaker, I knew I couldn't do it anyway. But all these adverts saying that every 20 seconds somebody wins £1,000, I was able to work out, knowing how much went into the prize money and how, etc., that every, you know, what did I just say? Every you know, minute somebody wins £1,000, that means that every minute 400,000 people had to lose £1, you know, to and this sort of thing. But I do find modern adverts some very confusing ones, mainly for I think hair products and things like this, where they say 79% of 49 people said, and you kind of think, well, what's the point in putting that on the bottom of the thing? You're much better, you know, having an actress or whatever, just, you know, lying and, you know, saying it makes them look pretty. But
Graham, when you talk about the beauty of maths, what do you actually mean?
Mainly a sense of wonderment. For the example I took of pi being involved with mathematics, it's in these 3 totally different ways, so unexpected, so miraculous in a way, and I'm just astonished at some of the things that I was just introduced to in my mathematics education. It's I think the main point which has come out of your contributions is the improvement which is needed is to make the learning of mathematics relevant to everyday life, rather than a separate. Hang on to that. Hattie.
Oh, I just had a terrific experience of learning maths, really. I don't remember learning maths in primary school, really, except it was the times tables and that was good fun. And then in secondary, I was 11, and that was called a middle school. But the teacher there was very visual and had cubes and columns and you know, matched them all together to show how they multiplied and fitted together. So it's very visual. I liked that very much. And we did matrices and we did about circles, and there was enough variety to add to knowledge as we went along, and have some fun with it, and being very practical and getting down on the floor, as you say, and putting things together. I really liked that very much, and that was for a year. So Barnes was very influential in my maths grounding, I think. And then, I can't remember the maths O-level bit at all, but I suppose we had to work out things that were supposed to be relevant, like field sizes and car dimensions and CCs and all that, to do with particular problems that would be set to us in the GCSE. And then I went on and did further maths, but we started, as soon as the exams were done in May, we started the A-level stuff. 3 of us that the teacher said, you and you will do A-level and maths. Oh, great, okay, right, here we go then. And the other 2 did further maths and A-level. I just did the A-level. And Eileen was just the most superb teacher, very different. I count myself as extremely lucky. And then, of course, we had statistics in when I was in university and studying medicine. I intercalated a social and political science degree course for a year. One of the papers was statistics, and I thought, gee, this is what I need for medicine, to understand what changes we might make. So I did that. It was great. Thank you very much for my say so. Thank you, Graham.
Well, friends, I think that is... oh, David, would you like to say something? You're muted, Graham. David. Graham, David, Graham.
Just to add one final thing in favor of the beauty of mathematics, I think we all find our limit, and Graham obviously finds great joy in the ways in which pi can be formulated. Depending on how your mind is constructed, I think there is no limit to the depth to which you can go with mathematics and still find it fascinating. Because what we've discovered, mathematics is the language by which we can intelligently and intelligibly understand the universe and express the laws of nature. If you can't express a law of nature in mathematics, it probably isn't a law of nature. And it's wonderful to watch, the great scientists and the great mathematicians present their ideas in ways that are intelligible. So, I would argue that we are probably not qualified as a group to decide on how we should best teach mathematics. But I would go back to the idea of citizens' assemblies and deeper democracy, and the idea of presenting juries of citizens with good information on something in order to make decisions on how we educate our children in future. But my personal vote would be for the critical importance of science, technology, and mathematics alongside the arts and the humanities. Let's just get better at learning and better at teaching. And that's up for grabs now, because with the way that we communicate in the world, everybody can have instant access to far better teachers than the one that you might have got thrown at you at random when you were a child in primary school. But thank you, Graham, for raising the topic and having us think about it.
Absolutely, yeah.
My friends, that would seem to be it for today, as we're losing people right. As we seem to be losing a few people at the moment. Right. Thank you, Graham, for your talk. And
yeah, thank you.
Thank you very much. Yeah.
And
Thank you.
next
Thank
week, just before summer break, we have David, who will be giving us a talk on energy transition, communities delivering net zero. A possibility, I think you would agree.
How to get climate change right.
Okay, thank you, friends.
Great.
Thank you.
Thank you.
Bye.
Cheers.
Well,